Everything okay?
Okay, so since this is the last part of my triple, I also want to once again you organizers for both putting together a conference and also for having me. So I ran out of time last time discussing the issue of order in the nuclides, discussing the issue connected to the spin density wave state and how to view the interactions which may or may not be responsible for its formation. And they started to discuss the issue about pairing from repulsive interactions in the superconducting state. So remember that the idea actually stems back to quite some time, is connecting that if the pairing of interaction is peaked at some particular wave vector, then for the two fermions who want to pair, or for the k-states involved, that if they're separated by this wave vector, we can get a solution to the gap equation where the gap changes sign. So in the Kruppritz, that gives rise in a single band to dx squared minus y squared, and then the idea is in the Nick-type, we could get a isotropic gap on the electron sheets and an isotropic gap on the hole sheets, but being of different sign. And so the issue here is nothing to do with orbitals. This is just Fermi surface. And so that's kind of a distinction about whether the superconductivity cares about having orbitals or not, or is it everything being determined by the Fermi surface. So let me go to here. So that the idea is then, based on bands alone, we would expect say an S plus minus state where the gap could be isotropic but of different signs. And if one of these pockets happens to disappear, say like the whole pocket at the gamma point, such as in the potassium iron selenide, then in order to satisfy this criterion, then we have to change sign going around just the electron sheets. And if that happens, then that's a dx squared minus y squared symmetry, again, based on interactions, which are based on just the band structure, the Fermi surfaces coming from the different bands. So I don't have time to go into the discussion about whether or not we can say superconductivity wins over magnetism. A lot has been done on that in the weak coupling problem from functional normalization group, and I gave a couple references here where that's discussed, so I'm not going to entertain that. That's an interesting subject matter in and of itself. But what I want to do is take a simple look at the Hamiltonian that introduced in the first lecture and it's been discussed many times in terms of what each of the pieces might do for superconductivity if orbitals are important. Okay? So if this is the Hamiltonian with the kinetic energy piece, of course that's just going to provide us with our band structure and then get superconductivity out of that. And then here's U prime, J prime. So reminding ourselves what these parameters are, the intra-orbit of U is a repulsive interaction between like orbitals. So that, of course, will penalize double occupancies if it's strong, but we might expect to get superconductivity from this term along, which involves sign reverse pairing of the same orbitals if they are connected by the peak of whatever that interaction is coming from, say, RPA or spin fluctuation theory. And that's different than U prime. U prime is a coupling between unlike orbitals, and so if U prime is the dominator, then you'd expect sign reverse pairing that's coming in connection with different orbitals. So there's a very strong connection between what U does, what U prime does, and that's what I want to kind of highlight. The Hun's J, of course, promotes spin alignment and likes to make things on a single atom line up. But if J is large, we have the approximate relation for spherically symmetric systems that J is related to the difference between U and U prime. And so if we've got a substantial Hund's interaction, then we would expect U prime to not be as large as U, and U prime could be, in fact, small. And if that happens, that if U prime is small because of a good Huns, which is compensating the on-site Coulomb interaction, then it is possible that it could set the stage for a pairing interaction which mixes orbitals. And that's where the electron-phonon problem can come back in, because the stage is set so that orbital fluctuations induced by the electron-phonon interaction could turn it attractive. And if it's attractive, then we're back to a conventional superconducting sort of picture and expect to get S++ pairing, if, of course, U is not too big to prevent the whole thing from forming.
Sorry, this is small and there. So how small has to be small? So in terms of like some quantity, like could that be like realistic, or let's say how large should be J Coulomb as a function of U, like?
I'm going to show a phase diagram in a couple slides. Okay. And then the other piece is this pair hopping piece, J prime. I kind of slid over this a little bit quickly during the other lecture. Since it involves taking two electrons and moving them to another, from one set of orbital to another orbital, of course, if there's a strong Coulomb interaction involved, that this would generally be penalized. It's not going to have a double occupancies from the effects of U and U prime. But it does provide a mechanism for you to mix states on different orbitals, and so that would, again, being contributing to a repulsive reaction, can promote sign reverse pairing of different orbitals. So we have two different routes to doing that, through U prime and through J prime. And so if you look at this from a broader perspective, if orbitals are playing a role, I have a good metric from which I can see which pieces are going to determine what type of pairing I can get. So, and if not, then the role of just the bands and the Fermi surfaces may be all we need, and we don't need to be complicated about orbitals. So let me discuss a little bit about that. So let's look at some results that a lot of people have looked at from a 5-orbital model, and look at the effect when the interaction is strongly coupling intraorbital repulsion. So this is a slide from Peter. So here are the bands with their orbital content. I'm sorry I didn't put the legend up, but the green and the blue represents different orbital content. And so if there's an interaction, that is a momentum of pi 0, so the green would be feeling the green, and you would expect then to have the gap form, which would be of opposite sign on those two pieces. So there's the blue, and here's the red on the inner part. And if interorbital is not so dominant, then you would not get as big an effect going from this outer piece to this outer piece. And the same if I look at the blue orbital component going either with the green or the red orbital component. So that is going to dictate an anisotropy of the energy gap going around, say, the beta sheets or the electron sheets and the hole sheets, because it's just a manifestation of this orbital character, this orbital inequality.
What is lambda in this book?
This is the eigenvalue that this is the leading pair symmetry. Okay, and so that could be different from the point of view of just saying, okay, instead of weak coupling, let's just look at strong coupling physics, where I'm just now not considering the Hamiltonian I've seen before, but just consider an effective Hamiltonian where all the orbitals have been kind of integrated out, and I'm left with the J1, J2 model. So if there's large J2, I'll have an interaction which would prefer to have connection between these spins along the diagonal as opposed along to the Brillouin zone direction of the axes. And so the pair state that I would get will depend on this magnitude of J1 and J2. And if J2 is big enough so that it gives me this type of antiferromagnetic collinear order, then I would expect to have a pairing which is anisotropic and is simply given by an A1G representation which goes like cos kx times cos ky. So here's a strong coupling view which is not connected to orbital physics, and it's just simply given by the effective values of these interactions, or the ratio of these interactions in J1 and J2. So here we have a pretty good way of trying to distinguish between weak coupling picture, which is being driven by the intraorbital repulsion, and one which is coming from a strong coupling point of view in J1, J2. And the real difference would be in, we look at, for example, the potassium, the XY2 compound, which has no sheet that's sitting in here. On one case, we would expect to get a dx squared minus y squared pairing for the case when everything is driven by intraorbital, or I'm sorry, from Coulomb interactions connected to the orbital. But in the J1, J2 model, then the gap is just given by this guy. So the J1, J2 would just give me a pairing which is going to be on the same side. So we're looking at this one and looking for the difference between, so both would give you full gaps, but the sign of the gap would change in this case and not change in this case. And because it's connected just to J1 and J2, another check would be to look at materials which have similar Fermi surfaces, because the location of where the Fermi surface is the piece which would be more interesting. Yes?
Sorry, I missed the difference between A1G, B1G.
Oh, so these are just the irreducible representations that are allowed by symmetry for D4H. So it's a mouthful, but these are all transformed. This one and this one transform according to the full symmetry of the lattice. Okay, so this is a constant would be allowed. Or something which is transforms like x squared plus y squared is allowed. X squared times y squared. Anything which I can use to build up something which maintains the fourfold symmetry. Okay. So they'll have different eigenvalues because they have different degree of anisotropy going on. Okay.
I think the question is that you have A1G Sx squared plus y squared and B1G Sx squared plus y squared. Top row.
And also second row.
Yeah. Top row. This one?
Well, you know, you have basically the same base functions for A1G and B1G.
And some of
Okay.
the basis functions look inconsistent with the representation.
Yeah.
Right, so please don't ask me to ask you. This is down here. I would never call this B1G. I would get killed by half of my collaborators if I did.
And in second row, you would call it A1G.
It's all A1G, anything that.
No, you don't call dx squared minus y squared A1G.
Yeah,
I mean,
that's
that would
right.
be sad.
I have a feeling that basis function probably refers to the local behavior of the function around the sheet. And the representation corresponds to how they transform into each other around the Brillouin zone.
Thank
But
you.
that's a guess, I don't remember.
Thank you, thank you. Yeah, I don't claim responsibility. Right, so, okay, so in anything connected with, trying to figure out what drives superconductivity, it's good to have well-defined predictions about what one theory does compared to the other, and make them as big and as separate as possible. So of course, detecting phases is not an easy thing to do experimentally, but at least theoretically, that's a crisp argument that would make a difference between the two scenarios. Okay, so here's the phase diagram that I said I was going to show. So this is a connection of work that's done by Compani and also another group in Japan, which is looking at what I said was a small interaction, which is the iron-arsenic-phonon interaction, which modulates charge between the iron and the arsenic. And if it's modulating charge between the iron and arsenic, it'll eventually go from iron to iron, and that'll be a strong orbital mixture of charge transfer mediated by the phonons. And so that this would give, there's various different types of modes or ways in which charge can be moved around depending on what mode one is looking at. And so here's the phase diagram, which is an electron-phonon coupling parameter here that'll promote forming an S-wave state, and here is the value of U that's sitting here. Here's a fixed U prime. Okay? So of course, if U is big, it's going to suppress having the charge fluctuation be uniform that you'd expect in just a simple S++ state. So here you have the same type of interaction that you would expect from the spin fluctuations, namely S plus-minus. But if U is small and the electron-phonon interaction is large, then you could swing over to S++ pairing. Okay? And so depending upon where you are in the phase diagram, nature it would be nice if nature fixed you over here or fixed you over here, but the real critical issue are lying along this line, so certain materials can be one way, certain other materials could be the other way.
So is the reason clear? So what is the reason results?
These guys? Yeah, I'm kind of colorblind on those. I don't know what the differences are, why one's green and one's
Sorry, how does along this line, how do I think about it? If I go from S++ to S plus minus, imagine I tune U. Does the amplitude of the gap vanish along this line and then I switch the sign, or is it the first order transition with a finite gap amplitude? So what happens if I actually fix, let's say, one of those things across the line? How do I go from plus plus to plus minus?
Well, I don't think that's been answered fully. I certainly don't know the answer to that, but I expect that of course that means that the eigenvalues are crossing one at the same time. And so you can watch, Peter's got his hand up, but you can watch the evolution as you go lower temperature when those eigenvalues cross. Go ahead.
Well, I've just seen the evaluation of the same theory, so I don't know whether you want to take it seriously or not, but if you do, then what happens is the S plus one of these isotropic states in either end of the phase diagram develops nodes, and then they go through and get deeper on the other side. So there are nodes along that diagonal line there.
So basically there is a diagonal stripe of nodal thing on electron pockets.
Yeah, and then it just becomes all of the same size.
Then you can just smoothly transform from S++.
Exactly.
So nothing abrupt.
I don't think there's anything abrupt that happens.
In this model, the presence of the Hund's coupling is just through the reduced value of U prime. There's no explicit spin alignment term.
Pardon, say again your last
And the presence of Hund's coupling in this model is just through the reduced value of U prime compared to U.
No, Hunt's is in there. It is parameterized again with U and U prime be related to J.
Okay.
It's the same Hamiltonian that they look at, but they just add electron-phonon coupling on top of it. In fact, it's even more complicated because they include the arsenic. So it includes more bands than just simple 5. Any other questions about this? Okay. And then another point that has been raised is the point of connected with pair hopping, and the S plus minus state can come from different orbitals. And so Jorg is here, I think he was here. Not here now. So he can comment about that. And the point that they're trying to make is that if you look at the Fermi surfaces, at least drawn at some particular level of doping, and I take this one and I try to move it on top of that one, then I will be more orbitally frustrated. That these are two different colors of orbitals that I would like to try to form a superconductor on, which is connected by pi 0. And so if you have a role of J prime, which promotes this interorbital type of pairing, then I can really lift off this orbital frustration and gain pairing from this J prime piece. So this J prime piece is important in that it takes the effective pair interaction, this is calculated within flex, and gives you as strong an interaction peaking at pi 0 as you could expect, or as you might expect from the inter and intraorbital pieces taken together. So if I could summarize, then basically you just saw what 4 pieces of that Hamiltonian could do, and particularly in connection to how electron-phonon may be actually relevant if the stage is set by having this U prime be large. So really the critical issue is to determine where, first of all, what are the strengths of these interactions? How big are U prime, J prime? How could we tell experimentally what they are? That'll certainly help to solidify the problem a little bit better and give more well-defined questions to ask. And of course, one of the interesting things to do is to look at the specific orbital dependence or the variation of the energy gap going around the Fermi surface and see how that looks in different materials as the Fermi surface changes. I've already pointed out that connection, say, between the J1, J2 model and the other ones which are more dependent upon orbitals. And the point I think that's been made is that there are very close eigenvalues where there's S plus minus and D wave pairing, which is lying not too far away. So really this means going and determining the gap structures for different materials and that the details really do matter. So unfortunately, as I said at the very beginning, the story is being written. There aren't that many would say there's some coming from photo emission, but not really that widespread reliable data on many different compounds that one could look at. And I'm going to leave that subject. I don't know whether that will be discussed in some of the later talks.
Has there been any phase-sensitive measurement like in detail?
No, there's been suggestions of how to do that, but none which have been pulled off. So let me just show this. This is just a kind of compendium that's put together from Cam Moeller on many different materials and measurements of the penetration depth, and looking at its temperature dependence and determining what can be said about the very low temperature behavior, meaning what is the existence of whether the nodes or can things be fit, connected to the observance of full gaps or not. So this was updated. You might have seen this before, but here are the 1,1,11,11 compounds, the phosphorus-based compounds, 11,11, and a whole family of 1,2,2 with different dopants, so different electron doping and hole doping. And so you can see that in some cases, you know, the one full gap doesn't seem to fit the penetration depth at all for any of them. So it's not just simple one gap fits all. Two full gaps at least has been seen in a couple compounds, and it's a little bit uncertain or in a number of different compounds.
Question,
Yes.
two full gaps means what exactly do I do? I
E to the minus delta 1 over t plus e to the minus delta 2 over t.
is
So
that
I fit inactivated behavior.
is it justified from a microscopic point of view? I solve a screening problem. I should have one length at the end of the day.
No, that's just a fitting to be able to determine what those delta 1s and delta 2s are. Which I think is completely reasonable. I think that you're fitting a low temperature dependent behavior. So then there's various different ways in which you could do that. That's one way.
That works for gaps that are completely decoupled.
Yes.
As soon as I couple them, there is one length that tells me at which distance I screen the
What
field.
do experiments know about being coupled or decoupled?
Well, this is Meissner effect. These are just two currents they're adding from the two different bands.
If they decouple.
No, they're... Okay, I'll get into this later.
Yeah. And then and looking for something which is really notable, which means the temperature-dependent variation of the penetration depth, that seems to be confirmed at least in the phosphide materials, in particular recent work on the 1 to 2 passing yield. So that seems to give, that's not too controversial. A number of different groups have seen that as being here. So that sense that there are nodes in some of these materials, particularly the phosphide, and there's been t-squared reports on many different other materials as well. And so it's not clear if t-squared is an effective power law, or is it d-wave plus impurities. That certainly is a little bit more that needs to be done to be able to understand what the t-squared means. Or is it a very, very anisotropic gap with a very, very deep minimum that sits in there that looks like t-squared. So, yes.
What does no comment mean?
No comment. I think that that's just a definitive statement can't necessarily be made, but I would ask Cam. I wouldn't award him. Okay, so basically for this part, I think that for both magnetism and superconductivity, there are many different ways of looking at it, and we haven't really converged yet on what is the best way. And sometimes I think it doesn't help to make things either one way or the other. Sometimes it helps to look at things from a point of view which includes both. I think that by and large, an itinerant approach, a decoupling approach to both magnetism and superconductivity seems to do rather well and give rise to an S plus minus pairing, which is driven more by the repulsive Coulomb interaction than by anything else. It's critical really to understand not just magnetism by itself and not just superconductivity by itself, but how do we go from one to the other. And I've really only reviewed each of them separately. I haven't looked at the interplay and particularly the role of coexistence of magnetism and superconductivity, which is there in certain regions of the phase diagram. And of course, the real issue is, can we separate out roles of nesting, decoupling, or strong coupling, and ultimately, as everyone asked, is how can you understand the material dependence and ways in which to make TC higher. So at this point, I'm going to depart from that, and I'm going to, from the review, and I want to discuss ways in which we can probe the interactions and determine, are we really, can we say from experiments if we are in a strong coupling regime, a weak coupling regime, and how can we pinpoint the interaction parameters? How much time do I have?
2 minutes.
All right, well, such is this. I will do my best. So, let's go back. So, I think I'll just kind of give you some summary of a couple papers that have been connected to this. This is work that we've been doing of looking at photon spectroscopies. I'm not going to talk about Raman scattering. I think Girish will cover that. But this is X-ray and photoemission work that we've been doing in collaboration with the group at Berkeley and Ziek Shen's group at Stanford. This was a snapshot, an older snapshot of people in a group, in particular Chinjing Jia is standing here, and she's sitting right over there. And Ian Fisher is providing samples, and Francois is a former postdoc, and Wei Sheng is the staff scientist at Science. So the idea is, if we look at photoemission, that if we just do a comparison of what you expect, or what you get in LSCO by taking a wider view at Couperet, a doped Couperet, and look at the photoemission, this is the integrated photoemission that you get in the 1111 compound, and do the same for another 1111 compound with phosphorus, compare that to LSCO, you see you have a very strong valence band connected with the oxygen degrees of freedom sitting down below the Fermi level, and a very tiny piece which is sitting at the Fermi level in LSCO. And if you compare that with the pnictides, you see a much bigger piece which is connected at states at the Fermi level. So qualitatively, it looks quite different, and here's the density of states from LDA, which is showing you that you just got way more states that are sitting at the Fermi level. And if you look at the photoemission coming from LDA, this is in the paramagnetic phase, and you try to move the bands around, you get a pretty good agreement if you can normalize the bandwidth by factor 2 or factor 3 with regard to LDA. So I think that the photoemission is giving evidence that we're not certainly in the realm of U being much greater than the bandwidth, certainly it may be near what the bandwidth may be. And that's been also corroborated with the optics measurements from Dimitri, who was supposed to be here, I thought.
In previous slide, can you show me once again what for you is really the good agreement? For example, that endpoint right side. Where is the good agreement?
Yeah, this is for
Close to endpoint.
this one here.
Yeah, where is the good agreement?
Yeah, right. Well, this is a particular photon matrix element that's put in right here. I hope Adam is going to describe a little bit more about this, so I'll defer to that to an experimentalist. It's not bad. Okay, and de Haas-Van Alphen measurements we've done by various different groups give masses that I said were on the order of 1 to 2 band masses or so. So we're in a region where U is not greater than the bandwidth. And that's similar to what we heard in connection to the mean-free pass on the different electron and hole sheets. So what I want to just talk about in the last 5 minutes or whatever is just what I said earlier on about how can we try to pinpoint UU prime, JJ prime from doing X-ray absorption. So what I want to do is to look at particular charge degrees of freedom on a particular site, a particular atom, in this case I'm going to do iron. So this is the big broad range of photon energies that are coming in, and each element has a specific edge corresponding to an atomic transition. In this case, it's kicking out a 1s electron in copper, a core electron in copper, and putting it into the 4p. If I zoom in on that particular state, I know that I'm going off of copper because that's the resonance. And if I look closer, I see wiggles. These are the X-aps wiggles. These tell me about the ways in which the bonds are coordination is connected to where copper feels connected to the ligands. And if I go closer, I have the near edge spectroscopy, so let's zoom in on that. And if I zoom in on that, then I start to be able to ask questions about what happens to the states that I'm going into as a photon comes in and makes a transition from at the L edge, from a 2p core level into a 3D valence shell. And so what we can look at are those absorption edges, the L2, L3. It's just going from the spin orbit split 2p1/2 into 3D, or the 2p3/2 into 3D. And basically what I'm looking for is I'm going to put an electron into this guy, and I would, if I didn't have any interactions to worry about, I'd be just looking at the unoccupied states, the states in which I could put an electron into as I'm going up. If there is a strong Coulomb interaction that's at play, then that core hole or the addition of an electron going from Dn to Dn+1 will shake up the spectrum and will look like nothing compared to what I would calculate from just the simple density of states effect. So basically the idea is, does everything look like you would expect from local density approximation, or are there shake-up or satellite features that come into play? So that, of course, was been used wonderfully in the context of Kupritz, and it's in fact what put teeth into the idea of Simon Rice and Sawatsky Eskis, thank you, about the idea of the basic building block of the Hubbard model, the Simon-Rice singlet. So this is X-ray absorption of LCO. This is the insulator, and when you dope, you see this low energy shoulder come up. That is exactly seeing the holes that you're putting into the oxygen, which form the Simon-Rice singlet. So that's this is very old work, but it really, for the students, this really is our building block upon which all Hubbard physics was built for the Kupritz. So here are the results that were carried out by the Berkeley group, and it's useful to look at iron metal. This is the L3 and the L2 absorption. That's going from 2p into 3d from the different spin orbit split states. And here are 3 iron arsenide materials, which look pretty much the same as iron metal. And now finally, I put back the hematite, which is what I said at the very beginning we were going to look at as the difference between the iron arsenides, the valence of 2+ and iron 3+. And here you see something which looks qualitatively different from these up on top. Here you have a peak followed by maybe a small shoulder, and another peak again followed by a small shoulder. And here you have well-defined 2 split peaks. So let's zoom in on that. So this was also work that was a different group which is producing similar type of results, which pretty much agreed with what you would expect from just LDA by itself. So in the interest of time, I'm going to forget the oxygen edge. So if you calculate the X-ray absorption from V2K, so this is the, the standard V2K package to calculate the absorption. It captures the line shape rather well, that basically what you're looking at is going into the iron unoccupied DDoS. And so this is for 122, the 1111, and another 122 with phosphorus that looks relatively similar to what you would get from the data alone, and qualitatively different from hematite iron oxide. Okay, so there are many different ways that can be calculated, but as I said early on, that the role of the U prime, JJ prime are manifest in all that multiplet spectra. And so you could look at the transitions from those multiplets as a way of determining the values of these parameters. So this is the 10dq splitting, and with the interactions, the 3D interactions, you get an obvious Lugano diagram, and depending on how big 10dq is, you can go from a high spin to a low spin state. And so you get an absorption feature, which is going to have peaks, which correspond for all of these different transitions, which are coming just from the single atom physics. So if you look then at what you would expect from the charge multiplets, you can look at the way in which 2 peaks get split off as you increase the value of the Hund's coupling. So I forget who it was, somebody said Hund's coupling is always 0.8 eV. It is always 0.8 eV, so in fact, let's make that even really big just by hand, and you see that this guy splits out, that this double peak feature is a measurement of that Hund's-like coupling. And so you could solve, in fact, the Schrodinger equation so you get everything all together at the same time. And so you really can describe this is the data that's in blue, and here's the dotted line with the Hund's coupling of 0.8 eV, which reproduces well the features seen in that spectrum. So we can then go from single atom physics to include hybridization with the ligands. I'm running out of time. So now I can start looking at a multi-orbital model. So here's UU prime, JJ prime all over again. But now I have a kinetic energy which is mixing the iron P states with the arsenic P states. And then I have also other things like this is a crystal field splitting and the core hole interaction. So I'm looking at going from the ground state, which is D6, and then D7 ligands and D8 double ligands into some final state with an additional electron. And I could look at the value of this charge transfer, this D6, D7 limit, and get another way of pinning parameters down. And so here's where U comes into play, because U is help setting the shoulder. This is the charge transfer peak of going on to the arsenic. And if U is made very, very large, this peak splits out and gets separated off from the main peak. So the location of the main peak and the shoulder is a way of ballparking U. And so we're able to give an upper bound, so U could be smaller than this, but it's certainly not more than 2 electron volts, because that would give you a spectral feature that you could sit on well separated from the main peak. And that's similar to another paper by Anisimov and Devereaux, who came to a similar conclusion. They had a slightly bigger J Hunds and a slightly smaller U, and also similar to what you would expect just for iron metal. So I think I'm going to skip the RICs and just go to the conclusions from here. It's not only our group, but it's many different groups of using X-ray spectroscopy have really put us using some numerical techniques into the situation where the Coulomb U is definitely smaller than the iron bandwidth. But the Hund's is still like it is for the atom 0.8 eV, which is quite substantial. So I'll stop there. Thank you.
Okay, so it's time for questions.
Did you point at me, Lenny? Thank you.
Yeah.
So from ARPA's and a little bit from Basil's work, there's a sense that if you go across the families in the pnictides, there's some significant variation in the degree of correlation. To pick some number, maybe some low energy band renormalization from 2 up until 6, or maybe even larger for the iron selenide material. And so I'm wondering, do we have from the X-ray a corresponding picture of the variation of U?
I've not seen any X-ray connected with the chalcogenons. I don't know if anybody
That
knows.
just hasn't been done yet?
It hasn't been done to my knowledge. Which of course is, if the samples are good, that's a very easy thing to measure. So that should be something which would be high on somebody's priority list.
Yeah, so these compounds will have a fairly amount of disorder, right?
Yeah.
So let's say the gap is S plus minus. Is there any explanation as to why it is so insensitive to disorder? S plus minus?
Yeah, that's a whole other discussion. Of
Repeat the
course.
question.
Disorder. If you allow me to rephrase it, is how could you expect a gap which changes sign to survive when you have disorder effects? And that's very important in connection to what I was saying about if the driver is connected to orbitals of the same orbitals or different orders, orbitals, you could say the same thing about the disorder and the role that it will have on this corresponding pair state. So if it mixes different bands, or if it mixes the same band, or if it mixes different orbitals, it mixes the same orbitals that could have different effect on things like the gap and TC. And so what we're used to thinking is in a single band language, that if you have an anisotropic S-wave gap and you put in disorder, it'll be washed out and give you something which is more uniform. And D wave hates having impurities involved as well violating Anderson's theorem. And that takes on a different language in multiband systems, and you have to really think about, look at the effects of what your impurity potential is really doing. And Peter, you may want to add some comment on.
I think that's the zeroth order answer. Otherwise, it's too
I can add
complicated.
one comment on that.
Yeah.
We do see that when you take families like the covalent fields, for impurities in plane, the C is much lower and you have a lot of extra scattering flow energies. And when you take the potassium family where the impurity is out of plane, you don't have scattering, basically, the output conductivity, for instance. So you do see a large effect of the impurities on the S plus minus picture. You shrink the gamma by a factor of 2 and TC by a factor of 2. The same way. So there is some effect. Maybe you don't destroy completely superconductivity, but you have a bit down.
I have a question. If U is not larger than 2 electron volts and JH is 0.8, so we have a ratio JH to U pretty large, right? Like 0.4.
Sorry,
J, like
H
who's
over
coming,
U. Yeah.
it's going to be quite large, so that's okay?
It's okay with me.
What worries
Is
you?
there no limit on the ratio we can have?
Well, I mean, if you drive U prime so that it goes completely negative, then you've got something which is unstable. So, you know, there are restrictions, you know, your ground state will switch and so on and so forth. But, you know.
Actually, this relation U minus U prime to J is, rigorously speaking, is valid only for isolated ions.
Yeah.
In, say, in solids and metal, especially, they may screen differently.
Robert?
If you use